Welcome to the Center for Energy Education's video series on energy storage. My name is Jason Bone, photovoltaics instructor for Halifax Community College. If you missed our first talk, I encourage you to take the time to view that video. At the end of the day, when it comes to energy storage and looking at solutions, it may be the most important part of the equation. The main theme of our first discussion was the concept that a watt not consumed was a watt that did not have to be generated, processed, or stored. We explored how much money we lose generating energy that we waste due to inefficiencies. Imagine the additional added cost to create storage for that energy that we plan to just throw away. One theme we will see today is based around the first law of thermodynamics, also known as the law of conservation of energy, which loosely states that energy can neither be created nor destroyed. Energy can only be transferred or changed from one form to another. We will certainly see this law at work throughout our discussion on fossil fuels. What are fossil fuels? Where do they come from? And how do we actually get energy from these fossil fuels? These are some of the questions we hope to answer today. Fossil fuels is a term used to describe a group of energy sources: petroleum or oil, natural gas, and coal. Chemically, these fuels are mainly composed of carbon and hydrogen, also known as hydrocarbons, with smaller percentages of oxygen, nitrogen, and sulfur. These fossil fuels are actually stored solar energy themselves. This solar energy was stored hundreds of millions of years ago. Plants, bacteria, and algae absorb this solar energy along with carbon dioxide and water. Through the process of photosynthesis, this ancient solar energy was used to split the water into hydrogen and oxygen. The oxygen was released back into the atmosphere. The hydrogen and carbon dioxide were stored in the plant as sugars and starches known as carbohydrates. Here we see our first example of the law of conservation of energy, solar energy being transformed into chemical energy. The process in creating coal began some 360 million years ago during the Carboniferous period, which spanned 60 million years. Vast forests covered the land during this time. Trees and other plants that grew in swampy areas died, and their remains got buried in the swampy soil. Over time, these remains were covered with layers of sediments like mud and sand. This created low oxygen conditions, halting the decay process. Due to the pressure of the top layer of dirt and water, the buried plant matter started to undergo chemical and physical changes, forming a material known as peat. Peat is still being formed today in bogs around the world. Peat has a carbon content of less than 60%. Over time, more and more sediments got deposited over the peat. This additional heat and pressure further compressed the peat between layers of sediments. These conditions pushed out more oxygen and water, forming lignite, which is often referred to as brown coal. Lignite has a carbon content of 65 to 70% and is the lowest grade of coal. As more heat and pressure were applied, more compression resulted in lignite transforming into sub-bituminous and finally bituminous coal. With a carbon content averaging 85%, it is used in making steel and electricity generation. Given time, pressure, and heat, bituminous coal became anthracite. With a carbon content of 95%, it is the highest grade of coal. The higher the grade of coal, the cleaner it burns. That is to say, the less soot, sulfur oxides, nitrogen oxides, and mercury it releases into the atmosphere. To add, the higher the grade of coal, the higher the carbon content. This means when burned, the higher grade coal will release more CO2, a greenhouse gas. Here we see a chart showing the number of pounds of CO2 released per 1 million BTUs of energy. We can see from this that the highest grade coal, anthracite, releases 228.6 pounds of CO2, more than any of the lower grade coals. From this chart, we can also see why natural gas is considered the cleaner fossil fuel, as its CO2 emissions are roughly 50% that of coal. And I couldn't help but throw some photovoltaics on the chart. Look at that CO2 emissions. 0. We'll be looking at renewables like solar, wind, and hydro in our next video. Before we move on, let me add one more thought. Most coal is delivered to power plants via train. So on top of the CO2 and greenhouse gas emissions of the coal, we need to consider the emissions of the diesel fuel used to transport the coal. The formation of petroleum and natural gas resulted from a process very similar to that of coal. Dead marine plants and animals sank to the seafloor, where they were covered by sand and mud. Over millions of years, they were buried deeper and deeper beneath layers of sediment and rock. This ever-increasing pressure and heat transformed them into oil and natural gas. Now that we have talked about how these fossil fuels were created, let's look at how we use them to create the energy we use to power our communities. The majority of the world's electrical energy is generated via magnetism through a process known as electromagnetic induction. To do this requires three things: a magnetic field, a coil of copper wire, and relative motion between these two items. In this demonstration, I'm holding a magnet and sweeping it back and forth, allowing the magnetic field to cut across the copper windings of a generator. Notice that the voltmeter registers a voltage as I do so. And here I've attached a magnet to a spindle that I can rotate inside the generator's winding. Notice that the meter registers 0 volts anytime there is no motion. Here we see another example of the first law of thermodynamics, or the law of conservation of energy. We are taking mechanical energy and transforming it into electrical energy. Let's explore how the chemical energy stored inside coal is transformed into electrical energy. Here we see the basic building blocks of a coal-fired power plant. From left to right, we see the boiler, the steam turbine, the generator, and a transformer. Inside the boiler, we burn the coal. When we burn coal, it requires oxygen to burn and releases the stored carbon within the coal in the form of CO2, along with thermal energy. This thermal energy boils water to create high-pressure steam, which is piped into a steam turbine. Here the thermal energy from the coal is transformed into mechanical energy as the high-pressure steam causes the turbine to spin. Next is our electrical generator. Its shaft is coupled to the shaft of the turbine. This is what gives us the motion required to spin the magnets past the coil windings inside the generator. Here we see the mechanical energy from the steam turbine being transformed into electrical energy. The voltage output from the generator is then sent to a transformer, an electrical machine that steps the voltage up to grid voltage, at the same time stepping down the current. The output of the transformer feeds the transmission lines, distributing electrical energy to the power grid. Let's compare the operation of a coal-fired power plant to that of a natural gas power plant. I think you will agree they are more alike than they are different. Here we have the basic building blocks of an open-cycle natural gas power plant. We don't see a boiler feeding a steam turbine, but instead we see natural gas being fed to a gas turbine. Other than that, we have the same components found in a coal-fired power plant. The gas turbine is connected to a generator whose output feeds a transformer, sending voltage to the power grid. Air enters the gas turbine via a compressor stage. This high-pressure air is mixed with natural gas in the combustion chamber of the gas turbine. Once the igniters fire, the fuel-air mixture combusts, causing the turbine blades to rotate. As in the coal-fired plant, the turbine shaft is coupled to the shaft of the generator, giving us the motion required to spin the magnets past the coil windings inside the generator, once again changing mechanical energy from the turbine into electrical energy. The voltage output from the generator is then sent to a transformer, stepping the voltage up to grid voltage for delivery to the power grid. And finally, let's take a quick look at a combined cycle natural gas plant. At numbers approaching 65%, it's the most efficient of the two. Here we see the basic open cycle system with one small but huge difference. The high temperature heat exhaust from the gas turbine is piped into a boiler to create steam. This steam is used to turn a steam generator, giving us even more electrical energy out, increasing the efficiency of the system. I hope you gained a little insight into the world of fossil fuels, what they are, how they were created, and how we use them to create energy to power the world around us. What took millions of years to create, we have used in a little over 200 years. Our demand for energy greatly exceeds the amount of fossil fuels, requiring us to look at other sustainable alternatives. I hope you'll join me for our next discussion on renewables. Until then, don't forget to turn the lights off.